All right, we are going to start describing the finite subgroups of SO2 and O2. Let me repeat again why we need this, because for applications like the molecules, for example, molecules like benzene, for example, we describe the symmetry as a subgroup of the rotation group. But in all of these cases, at least in most of these cases, the subgroup is a finite group. So it just has some finite number of elements. So as a result, we would like to understand how many such subgroups are there. How can we describe these kind of subgroups? So we need to do this, of course, in 3 dimensions, obviously, because these are all 3-dimensional things. So I'm going to do that too, but at least the parts for the finite subgroups of in 2 dimensions, subfinite subgroups of O2 and SO2, these are very simple. So as a result, I'm going to start with this O2 and SO2 basically. So I'll start with SO2. So let's say that G is a subgroup of SO2. So the number of elements, the order of the group, is a finite number. So that's basically what we are looking for. So for SO2, of course, that means that the group is formed from elements of the form R theta, where theta is some, is in some set of numbers. So in that case, this manifold structure that we have described becomes useful. So let's just remember that. So we have a starting angle in here, theta equals 0. So in that case, we basically have some set of points on that circle, and the rotations corresponding to this set of points somehow forms a group. Let's remember the group axioms. So first know that the identity is in there. So this is within the group, right? So that means this point theta corresponding to theta equals 0, so therefore should be within that set. Another thing, so we know that r theta, the inverse of a rotation is equal to r minus theta. So that means, let's say it like this, if r theta is within the group, then r minus theta is also within the group. So that means if I have a point in here somehow corresponding to angle theta, then a point corresponding to angle minus theta should somehow be within that set. And finally, of course, if r theta, if there are 2 rotations within the group, then the rotation corresponding to the obtained by taking the composition of these 2 rotations should also be within the group. So these are the basic group axioms. In any case, one special implication of this thing is that if r theta is within the group, then all the rotations that are obtained from this element only, right? Basically, all rotations which are an integer multiple of theta should be within that group. So this is an important starting point. So as a result, this is what I'm going to do. So I'll just say that, right, this is my manifold in here. Let's say theta equals 0 corresponds to this. So let's say that theta, I shouldn't use the same symbol for representing the symbol. So let's say that the 0 corresponds to identity. Let's say that the rotation with the smallest angle is theta. So that means the rotations corresponding to 2 theta and so on, 3 theta and so on, they are all within that group. So I'm just going to just mark some points in there. So how many, that doesn't matter. So let us suppose that, basically, if theta is in there, then an integer multiples of theta should be within that set, within that group. So if it appears that there is also some angle in here, let's say somewhere in here, between 2 theta and 3 theta, let's say this angle is phi, in this case, it appears that if phi is in there, then I know that R2 theta inverse in composition with R phi is basically a rotation with angle phi minus 2 theta. But in that case, phi minus 2 theta would be an angle somewhere in here, which would imply that there's also a rotation with an angle smaller than theta, which is against what we have assumed before. So this implies that there cannot be an angle apart from these integer multiples of theta, basically, right? So this kind of is a proof that all of the rotations within that group is just then obtained by r theta. So one particular implication is that, of course, this r0 is essentially an integer multiple. So therefore, r theta to the power, let me use little n in here, has to be equal to r of 2 pi. So that's equal to the rotation by 0. So that's equal to identity, which then implies that the group is basically the group of rotations obtained by r theta and taking powers of it. Right? So therefore, the largest power would be r to the power n minus 1 theta. That would essentially correspond to a rotation by minus theta. Right? So if that's the case, in that case, theta would be equal to 2 pi divided by n. Right? And in that case, the group is this group. And you can see that this group is a cyclic group. So G is a cyclic group which is generated by r theta. By r theta. So you can express all the rotations within that group by as a simple power of that fundamental group. Right? In that case, we just say that G is isomorphic to the cyclic group. But in general, of course, people use this Cn notation to mean particularly that group. So as a result, whenever I say Cn, I'm just going to mean that particular group. Cn, therefore, in the context of rotation subgroups, is a group formed by a rotation by an angle of 2 pi over n and all the rotations that can be obtained from it. So as a result, it's a group with order n. So let's just remember that this Cn is isomorphic to nth roots of unity. If you remember, we had a discussion about this before. We can also describe the nth roots of unity in the complex plane as some complex numbers on the unit circle. You can see that we basically have the same description of these numbers or the rotations that are in here. Also, just remember that these are also isomorphic to integers with addition modulo n. This is also going to give us the same group structure. Let me pause a little bit. All right, so in any case, this is a group that we are familiar with. So let's just remember that Cn is commutative, is abelian, which means conjugacy classes are the, we know what the conjugacy classes are. Conjugacy classes are basically the elements of the form like r theta to the power k. So each element would form a conjugacy class. So as a result, at least for that group, that description is simple. So since it's abelian, things are very simple. So let's then look at this case where G is a finite subgroup of O2 this time. So G may or may not contain improper elements. So there are these two possibilities. The first one is that let's say it like this. G has only proper rotations. this is basically the previous case that we have described. So therefore, G is a subgroup of SO2. So therefore, G is basically the cyclic group. Right, it's a cyclic group for an integer n. So therefore, we look at this other possibility. So G contains improper rotations. If that's the case, in that case, half of the elements of G are proper and other half improper. Why? If you think of it as a formal proof, you just think about this homomorphism, which is basically the determinant from the group to the numbers +1 and -1. So this basically attaches these numbers +1 and -1 to the group elements. But in any case, the kernel of that homomorphism is basically the set of, this is the kernel of determinant, is the set of rotations in the group which are proper. And the remaining thing is basically the set of elements that are mapped into -1. This must be the coset of that kernel. So we know that each coset contains exactly the same number of elements as the kernel. So this kind of thinking basically shows that the group should have an even number of elements in that case, and exactly half of them would be proper, and exactly the other half should be improper. Okay, so the next thing is this. Once we establish this, so let's just remember that this kernel is formed from proper elements. So therefore, the kernel of this determinant should be isomorphic to Cn. So, I mean, because this is a subgroup of SO2, sorry about that. So that means, therefore, G should contain, therefore, first rotations by some angle theta. Let me just write it down like that, n-1 times theta, where theta is essentially a rotation by 2 pi n. Okay, so that means n elements are proper. These are the proper elements of the group. And then there should be some improper elements in here. So these are basically rotations by some angles. And there should be, reflections by some angles, phi 2 and so on. And there should be exactly n of them. Okay. So I'm going to start making, it's not an assumption actually, so we can actually choose one of these angles to be equal to 0, because this angle describes the angle of the mirror plane, mirror plane, this phi 1 describes the angle of the mirror plane with respect to the x-axis. So if I redefine my axes such that this mirror plane coincides with the x-axis, that's equivalent to choosing this angle to be equal to 0. Right? So as a result, you can therefore choose this one to be equal to J0. So it's just a reflection along the y direction. You can think of it like that. So as a result, let me then erase this and then call this as J0. And now I can see that I can obtain all the other reflections. For example, J phi 2 as this first reflection succeeded by r theta. And the second J phi 3 would be J0 succeeded by the rotation by 2 theta and so on. So therefore, it is apparent that these are essentially reflections with angles. I'm just going to write them down like that. Angles theta, J of 2, let me erase this and then write this better. Reflection by 2 theta and so on. Up until the last one, the reflection by n minus 1 theta. So as a result, our group is a group like that. Right. So mathematical description like that is not that helpful actually. But I'm just going to say that this is called the dihedral group. N is a parameter that describes the group, but let's just say that the order of the group dn is equal to 2n. So basically, n describes the rotation subgroup of that group basically. So the n elements correspond to the rotations, including the identity, and the other n elements correspond to reflections. So we can also describe what the reflection planes are, but probably the best way to describe that group as the symmetric group of a regular n-gon. So symmetric group of regular n-gon. The shape itself says something about the group. So I'll start with this D3. D3 is the symmetric group of a triangle. In that case, this is kind of triangle. Apparent what the symmetry operations are. First, the operations, the symmetry operations are the rotations. So we have these 3 rotations. Essentially, identity is in there for the rotations. Rotation by 120 degrees. So instead of radians, let me write down angles in here, or let's just forget about it. So 120 degree rotation, that means is a rotation by 2 pi over 3 radians, and a rotation by minus 2 pi over 3. So these are the proper rotations. In a way, this basically is a rotation that takes this triangle and moves the each corner to a succeeding corner or a different corner, but it just does this in a cyclic manner. Right? You can think of it like that. So these are the rotational symmetries. So that's actually the 3 elements of D3. And there are these 3 other elements. So these are the reflections. So in that case, the reflection planes are like these. These are the reflection planes. I can also write down the angles of these planes, but that kind of a description is not that helpful. In any case, you can see that therefore in here there are 3 reflection planes. Somehow it coincides with the number of corners, but that's just a don't get confused by this thing. So let's just take this reflection plane. This is a mirror plane basically. This is an operation that exchanges these 2 corners, and so therefore it leaves that particular corner invariant. So this is a group that we have met before, and I have said that this group can be actually equivalently described as the symmetric group of permutations, all permutations of 3 objects, because somehow this set of operations somehow exchanges all the corners of the triangle with each other. So for every possible permutation of the corners of the triangle, we have a corresponding rotation or a reflection in the symmetry group, right? So that's one case. So D3 is basically non-abelian. So as a result, this is also something that we have said before. So this is also a group with the it's the smallest group, smallest non-abelian group. So that's why we have talked about this. I'm going to come back to D2. So just wait for it, and perhaps D1 as well. So let's just skip D1 and D2 in here. Let's start with D3 and then pass to D4. So D4 is the symmetric group of a square. Okay, in that case too, the group have these rotational symmetries, of course, by 0, which is identity, by 90 degrees, by 180 degrees, pi, sorry about that, 180 degrees, and 270 degrees, which is like minus pi over 2. So basically these are the proper rotations that map the square to itself, and then there are these reflections. For these reflections, I think I'm going to draw solid lines. So we have these 4 mirror planes. Interestingly, in that case, 2 of the mirror planes, I'm going to draw this again. So 2 of these mirror planes, let me use a different color in here. This one and that one, they pass from the corners, but this mirror plane and that mirror plane, they pass from the midpoints of the edges. Right? We didn't have this kind of a situation for D3. In D3, all 3 mirror planes were passing from the corners and midpoints of the edges. That's an interesting twist, but I'm going to explain the meaning of this later. All right, so that's as simple as that. So therefore, there are 4 reflections and 4 rotations. So it's obvious that D4 has an order 8. Now you might think that, well, is D4 the same thing as S4? No, it is not. Well, S4, basically the permutations of all corners of permutations of 4 objects, the number of elements is equal to 4 factorial, which is 4 times 6 is 24. So therefore, it's obvious that D4 is not the same thing as S4. But just keep in mind that D4 is a set, is also, I mean, the elements of D4 can also be thought as permutations of the corners of this shape. So as a result, D4 is a subgroup of S4. So you can really see that there was a theorem that says that the order of the subgroup actually divides the order of a group. You can, well, see that 8 basically divides 24. So that actually kind of confirms this thing. So it's just an example of that theorem actually. But in any case, it's a proper subgroup of the full permutation group S4. But again, I mean, we can think of D4 as permutations of the corners, but it's a permutation that somehow preserves the succeeding corners. So we know that, for example, let's say this corner and that corner, they somehow succeed each other. So it's just a set of permutations that somehow preserves this relationship. So as a result, it doesn't map, for example, these elements to opposite to the diagonals, for example. In any case, let's just keep in mind. So we can continue. S5. D5. D5 again is the symmetry group of a regular pentagon. It's not a good pentagon, so let me try to draw something like that. So in any case, so there are 5 rotations, 5 proper rotations. And 5 reflections in here within the group. So again in here, if I draw the reflections, so reflection planes, the mirror planes. So each mirror plane passes from a corner of the shape and the midpoint of the edge. So that's also a case like similar to the triangle. So in each case we have a similar kind of a situation. All right. Again, there are 5 mirror planes. You can count that. So therefore, D5 has an is a group with order 10, and we have this structure. All right, so let's then come back D2. D2 essentially contains two rotations, which is basically rotations by, one of them is identity and the other one is a rotation by 180 degrees, and two reflections. You can think of it like that. So you can think of it as a symmetric group of a two-gon, but there's no shape that's called two-gon. But luckily there's a shape where this D2 can be considered as a symmetric group. Oh, that's basically a rectangle. So D2 is the symmetric group of a plane rectangle, right? Of a rectangle. In that case, of course, there are two rotations. One is identity and the other one is the 180-degree rotation like that. So that's one element. And then there are two mirror planes. So one mirror plane is like that. It basically exchanges these two corners and these two corners. And the other plane, mirror plane, is like that. We have seen this group in the past. We have just called the rotation as A. I can describe it like that in here. I think I'm going to do it like that. So A is the rotation around this midpoint of the rectangle in here by 180 degrees. We just call one of these reflections as B and the other reflection as C. Interestingly, in that situation, since the rotations are the only non-trivial rotation is 180 degrees, all of these three operations commute with each other. So as a result, D2 is abelian. So it's the example of a dihedral group which is abelian. So in, at least for 2, it is abelian group. D2 and D1 is also abelian. But D3 and higher order dihedral groups, they are all non-abelian. So let's just remember that in that group, we have this simple, very simple product rule, AB is equal to C and things like that. In any case, you just remember that, just forget about the rectangle. This was the symmetric group of the water molecule. Actually, in the water molecule, there were actually two reflections and 180-degree rotation, if you remember. So as a result, this is really the symmetric group of the water molecule. In any case, D1, I can still define a D1. So in that case, of course, the only rotation is just the identity, and there is just a reflection in here. So that's kind of the simplest one, where we have the only non-trivial operation is the reflection. So that's also one of the things that we have seen perhaps in this double oscillator problem, for example. In any case, you can think of it as this kind of a symmetric group as well. But if we just make this exception of D1 and D2, all the other groups, dihedral groups, are non-abelian. Dn are non-abelian for n greater than or equal to 3. So as a result, for these kind of groups, we need to understand the conjugacy relationship. So how do we describe the conjugacy relationship? Because it's not that simple. So I'm just going to say something about it in here. So let's just say show the elements by x and y, right? I'm not going to use j and r expressions in here. We say that x and y are conjugate. Let me use this notation in here, sorry about that. X and y are conjugate if x is equal to z times y z inverse for some z in the group. Right? Let's just remember this. One implication is that, so if you just look at the determinant in here, if two elements are conjugate, therefore their determinants should be the same, which implies that the proper rotations are conjugate to proper rotations, and improper rotations are conjugate to improper rotations. So as a result, there is no way that a proper rotation can be conjugate to an improper rotation. So that's the first thing, right? So that's one of the rules. Rotations are conjugate to rotations, and reflections are conjugate to reflections. But which rotations are conjugate to which ones? We can also say it like this. So let's start with the rotations. Let's say it like this. So r theta is equal to z times r phi z inverse, or something like that. So let's say that we have this kind of a conjugacy relationship. Now there are these two cases. Z might be a proper rotation, or Z might be a reflection. Okay, if Z is a proper rotation, in that case, this Z minus 1 R phi, sorry about this, I need to use another symbol in here. So let me use a third angle in here. So I'm going to call this as R alpha. So in any case, what I was going to say is this. So if Z is a proper rotation, we know that all the proper rotations are conjugate to each other. All proper rotations commute with each other, which therefore implies that Z inverse R phi Z is equal to R phi. So basically, in this case, Z cannot change the angle in here. So as a result, what we get is we always get R phi. So if we use all the possible proper rotations within the group, I'm not going to get anything new. So I'm just going to get the same element. So we know that same element is an element is conjugate to itself. That's it. What happens if I use a reflection in here? So in that case, let's say it like this. J alpha can be written as, I mean, we have done this before, so I'm just going to keep this short. So we have seen that this expression is equal to R minus phi. So therefore, if we do a similarity transformation with a reflection, then I get a rotation in the opposite direction. So I basically get a rotation by minus phi. Okay. So therefore, as a result, if R theta is conjugate to R phi, then the angles are either equal or just opposite. So let's just say it like this. I'm sorry about that. I'm going to use the double implication thing. So R theta is conjugate to R phi if and only if either the angles are the same or the angles are opposite. Which means the conjugacy classes of rotations are basically a rotation by theta and rotation by minus theta. Its inverse forms a conjugacy class. Okay. So next. So these are basically for proper rotations. Yeah, I should have said proper rotations in here. Sorry about that. So proper rotations are conjugate to proper rotations only. and the reflections are conjugate to reflections only. So next, let's then start describing the conjugacy relationship between reflections. So let's say J theta is a reflection, and I'm interested in the conjugacy relationship in here. So this is a little bit complicated because, I mean, you can actually do the algebra again in here. So you just let, for example, this thing to be, for example, equal to a rotation and see what happens, and take z to be equal to r minus alpha and sorry about this, j alpha, and see what happens. Okay, you can do the analysis in here, but I'm just going to do it like that. This is actually a much more fruitful way of thinking about it. But I mean, let me just quickly do this for, I don't know, let's say R alpha. So let's say it like this. R alpha inverse J phi R alpha. What is this? So that's basically R of minus alpha J phi R alpha. And then we have said that this is, I can change the place in here by making the sign before the angle to be negative. So therefore this is a rotation by minus 2 alpha J phi. So therefore this is a basically a reflection with an angle of phi minus 2 alpha. Okay. So in any case, as a result, a reflection is conjugate to another reflection if the difference between their angle parameters is twice a possible rotation angle. But this also implies that, if you remember, theta over 2 was the angle of the mirror planes. So if the difference of the angle between the mirror planes is actually, let's say it like this, this is phi over 2 minus alpha. If the angle difference of the angle between the corresponding mirror planes is an integer multiple of, or is just a rotation angle, a possible rotation angle within the group, in that case, these two operations are conjugate, right? This is a very nice geometrical way of expressing it. So I'm just going to do it like this. So let's just draw this pentagon shape in here. So I have one mirror in here with a plane like that, and another mirror somewhere in here. So I'm going to just show this with dot, dot, dot. So this might be J theta and this might be J phi, right? We say that J theta is conjugate to J phi if and only if, sorry about that, if and only if, right, there is a rotation within the group which rotates the mirror plane of J theta to the mirror plane of J phi. Okay, at least for the case of pentagon, this is very simple because we have rotations that rotate this corner to that corner to any other corner. So as a result, since all the mirror planes are passing from a corner and a midpoint, so as a result, this then implies that in D5, for example, all the reflections are conjugate to each other. Okay, but we don't have this this thing for the D4, for the symmetric group of a square. So in D4, for example, we have two types of mirror planes. So there are these mirror planes that pass from the midpoints of the edges. I'm going to use a different color now, green color for example. And then we have mirror planes that are passing from the corner. So therefore there is no way that there is a rotation that would rotate one of these green lines to one of these yellow lines. So as a result, there are these two inequivalent sets of mirror planes, therefore. So therefore, I'm just going to do this. For example, in D4, what are the conjugacy classes? Conjugacy classes in D4. I'll start with the, of course, the identity. So identity is a conjugacy class by itself. In D4, there are actually 3 non-trivial rotations. 2 of these rotations are by 90 degrees and by minus 90 degrees. These are conjugate to each other because they are rotations by 90 degrees, but in opposite directions in a way. Somehow they are conjugate to each other. And there's a single rotation with a rotation angle of 180 degrees. So 180 is the same thing as minus 180. So therefore, this element is conjugate only to itself. And then there are these 2 mirrors. I'm going to name them like this. Sorry about that. Yeah, I'm going to name them like this. So let's say that A is the reflection with this mirror plane, B is with this, C is with that, and D is with that. And this is essentially the same as this one in here. So as a result, there are 4 reflections. So we can see that in here, for example, A and C are conjugate to each other, but A is not conjugate to B. And B and D are conjugate to each other. So as a result, in D4, in the dihedral group D4, there are 5 conjugacy classes. Keep in mind that this also implies that D4 has 5 different irreducible representations. Let's go and talk about D3, because this is something that we already know. We know that D3 is isomorphic to S3, and we have talked about the conjugacy classes of permutation groups before. So let's talk about this. So let me just start with this, the conjugacy classes. There are 3 rotations again. One of them is the identity. So that's conjugate to itself only. Then there are these 2 other rotations by 120 degrees and minus 120 degrees. These are conjugate to each other because the magnitude of the rotation angle is the same. This is only in dihedral group, by the way, so that rule is only for dihedral group. So these basically exhaust all the rotations, and then we have the reflections. In that case, we just draw the mirror plane. So that's the first one, second one, the third one. Just label them by A, B, C. So we have these 3 operations in here. So therefore, these 3 are all conjugate to each other because by rotating any of these mirror planes, I can obtain any other mirror plane. All right, these are the only conjugacy classes. So how do they correspond to this S3 in here? Just remember this. So I'm going to use a blue color in here. So we know that, of course, in that case, I can also consider the group as the group of permutations of the corners. So let's remember that the identity is identity. We had the same conjugacy class in here. 120 degree rotations. These are essentially permutations. 120 degree permutation basically corresponds to the permutation 1, 2, 3, where 1 is mapped into 2, 2 is mapped into 3, and 3 is mapped into 1. So it's just a rotation like that. And the other rotation is just the 1, 3, 2. So therefore, these 2 rotations are actually the 3 cycles. Okay. How about ABC? A basically is a reflection which fixes the element 2 and exchanges 1 and 3. So therefore this corresponds to the transposition 1, 3. B fixes the element 1, the corner 1, and exchanges 2, 3. And A does the fixes 2. Sorry about that. C fixes 3, and so therefore exchanges 1, 2. So therefore this conjugacy class corresponds to the transpositions or the odd permutations in the permutation group. In any case, so we know the conjugacy classes. So I mean, the groups are different, of course, in terms of their mathematical meaning. One is a rotation group and the other one is a permutation group, but they are isomorphic. They have the same structure. So therefore, the representations, the irreducible representations, are going to be the same. So, of course, we also remember that there are these two one-dimensional irreducible representations. One is the, of course, a trivial representation. The other one was the signature function, if you remember. So it just associated to all reflections or to all transpositions the value -1 and +1 for all the proper rotations. We have essentially the same thing for all dihedral groups as well, more or less. But I mean, this structure of the conjugacy classes is not that trivial, so there are some complications in there. So we have to keep this in mind because these are the groups that we actually meet a lot. So as a result, we use this kind of an information about the conjugacy classes to say something about the irreducible representations. So that's going to be the end of the finite subgroups topic. So let's just remember that basically finite subgroups. Subgroups of, let's say, O2 are basically either the cyclic group. This is basically abelian, so therefore it has known representations, all one-dimensional representations, or the dihedral group. So these are actually groups that we meet a lot. So as a result, we're seeing something about their structure in here. Okay, so the next topic is basically we are going to say something about the operations in the SO3, in the group SO3, and then we are going to say something about the finite subgroups of SO3.